Right, here we go. Third part of 2.4. A little more fun with chain rule and logs still. So what you're seeing in this one is how do we take the log of something like a to the x. All this is going to go back to log rules. I'm going to do a brief explanation on that, but we'll get it right into the rules for the derivatives. So far we've seen things like if I were to have x to the fifth power, and we use our exponent rule where you multiply the 5 to the front, but then you subtract one from the exponent. Well, how do you do that if your exponent's a variable? So if I have something like this, I can't just multiply x to the front and then subtract one from x because we don't know what x is. So that's where we get these other rules. If this was e to the x, well, we have rules for that. We know the derivative of e to the x is simply e to the x. But what do we do when our base is not e? And so that's where some of these other rules are going to come into play. One of the rules that you learned way back when you were doing logs is if I have e to the natural log of anything, if this is my base of e and this automatically has a base of e, when those guys were the same, this simply became my answer. And so that's where this rule stems from, is think of this as having that base of e. And so whatever was left became our answer. And so we have our a to the, this would be an x power. And so that's where this comes from. And so for the rule, it's like we're working backwards. So a to the x can be written in this form, and that's going to allow us to take a derivative on that, right? Because e to the derivative of this, derivative of e to the anything is e to that item times the derivative of the interior function, and that's where this first rule comes into play. That looks like this one right here. And so when you take the derivative of a to the x, it becomes the natural log of a times a to the x. Okay, and so that's going to be our first rule right here. So if we had, it always makes a lot more sense if you have some real numbers. For the most part, this is just going to be a rule you're going to have to remember for when you're doing stuff like this. So if I said, let's take the derivative of 8 to the x, again, I can't just multiply the x to the front and then subtract one from this because we don't know what this is. So instead, we're going to apply this rule to it. And so we're going to say if this was the natural log of my base times the whole thing. So again, I'm going to take the natural log of my base times the whole thing of a to the x, or 8 to the x. And we're going to get this look right here. And that's as far as it's going to simplify for us. Most likely, you'll probably see the 8 to the x written in front of the natural log. That tends to be the more common format for it. Just to spin off of that, and this is where the chain rule comes into play. If you have something more than just x, so whatever this u represents, this could represent 5x, it could represent x to the third, whatever it is, we have to remember to multiply by the derivative of that interior function, and that's where this comes into play. And it's just, again, one of those things you have to remember to look for. So here's another look with that right there. So again, we're going to take, this is a base to some unknown power. And so according to this rule right here, we take the natural log of the base times everything. So my base is pi, so we're going to take the natural log of my base, which is pi, times everything, which is pi to the x squared plus 5. And then here's where that extra piece comes into play by the chain rule, is we have to remember to multiply by the derivative of that interior function, which is our exponent. So we have to remember to multiply by the derivative of this interior function, which is 2x. And so that look right there is going to be the entire answer. As ugly as it is, that's as far as it can simplify. So let's jump on down to this one. This is another rule. These are really the same rule. This is something that I would just say if you're going to memorize anything, memorize this one. Right? Because you always want to look for a derivative of an interior function if it has one. If it doesn't have one, then great. This is all you would have to deal with. The second rule that we're looking at, and again, this is going to work out the same way. These are really the same rule. This is the one I would really have you memorize, because if there is something more than just x right here, we always want to look for that and remember to multiply by the derivative of whatever this interior function is. Right, and that's what you're seeing right here. This all goes back to something called the change of base formula. And I'll give it to you right here. So we said if I have the log base A of x, I can always write that as the log of this over the log of this. That was our change of base formula. So you could write that as the natural log of x over the natural log of A, or you could separate them to look like this. Either way, this is really just trying to give you some explanation as to where the rule comes from, so that maybe it will help you remember the rule, right? And so again, we're just doing our change of base formula on this. So we're going to rewrite this as the natural log of x over the natural log of A. So I get this look right here. And then now here's what we got as we're doing the derivative of that. So remember, the natural log of x is just 1 over x times, and here's what's left, is my 1 over natural log of A. And so if I put all that together, I get 1 over x natural log A, right? And that becomes our look. And so if I said, let's do the log of base 5x, so we're going to get that same idea right here. So again, if I did my change of base idea, I have the natural log of x over the natural log of 5. So it would look something like this. Right, that's our change of base formula. So we know the natural log of x is simply 1 over x. I already have the natural log of 5 down there, and that's going to stay right here. Remember, this is just a constant, so nothing to derive on that one. And so that's where that one would finish. This is the same rule, but now we're going to get something here more than just x. So again, we have to remember to multiply by the derivative of that interior function, and that's what this notation means, right? This is just your reminders to multiply by the derivative of the interior function. So in this case, again, we have natural log base 10 of the cosine of x. So now our interior function is the cosine of x instead of just x. And so we have to remember to multiply by the derivative of that interior function. Let me kind of break it down by what we did earlier. So I can rewrite this with my change of base formula as the natural log of the cosine of x over the natural log of 10, which would look like that right there. So again, it's the natural log of the cosine of x is just 1 over this item. So I get 1 over the cosine of x. My natural log of x, it's already down there. Sorry, that should have been natural log of 10. My bad. My natural log of 10 that's already down there is going to stay. It's just a constant. And now here's the extra step. I have to remember to multiply by the derivative of my interior function. And the derivative of the cosine of x is negative sine x. And so we get this look right here. This is one that you can simplify a little farther. Right? We know sine over cosine is tangent. And so it could clean up to look like this. So just a couple differentiation rules that we got to hang on to. So this is just to link it back to rules that we've learned in the past that associate with this, but why there's something a little more with this when your base is not E, right, when it's A instead. So if I were to use the same idea with this one, we've already learned that the derivative of E to anything is that item. So the derivative of E to the x squared is simply E to the x squared times the derivative of my interior function, which is 2x. But with this one, right, that's all I would need, right? Because if I keep the rule that we just learned with my natural log of the base included, well, the natural log of E is simply 1, right? And so I don't need the extra part when my base is E. However, when it's anything other than E, and so we're putting A there instead just to represent anything other than E, right, then we need it, right? And so that's when we get the examples that we just looked at in the previous lines up here, okay, where you do have to keep the natural log as part of the answer. Okay, and so here's just another example on that, so you can check that one out. Let me jump over to the next page here. All right, so I actually get to plug in some real numbers here on this one. Get this cord out of the way. All right, so in this case, now we have y equals my base of 9 to the 3x minus 4 power. So remember the rule we just looked at on the previous page. So since we're doing a base that's not E, right? And we have an exponent involved in or a variable involved in our exponent. So we just said on the previous page, and this is the rule that you want to remember with these, is it becomes, the derivative becomes, so we have the natural log of a to the u times a to the u times the derivative of that interior function. So it's going to play out something like this. And so I have my natural log of my base. Sorry, this was just a. So I have the natural log of my base times a to the u, which is 9 to the 3x minus 4, times the derivative of that interior function, which is just 3. And then whatever we can do to clean these up a little bit, we can do. So this one was because these could be written as a common base with both a base of 3. So they changed the 9 to 3 squared. So it became this look right here. And now I have base of 3 times a base of 3. So remember, the rule is if I'm multiplying common bases, I add their exponents. So if you think of this as 3 to the first, then I can keep my common base of 3. And if I did 6x minus 8 plus 1, I can get this look right here. So sometimes you'll see those altered to look like that in order to simplify and combine some of those terms together. So we could write it like this. All right, let me jump on down to this one. All right, so again, I now have a little product rule going on here. So x times 5 to the negative 3x. So here's where we're going to say our first times the derivative of the second. And so this is where you got to keep in mind, okay, well, how do I take the derivative of that second term, right? And this is that same rule that we just looked at up above, where we're doing our natural log of a times a to the u times derivative of that interior function, right? And so this is the rule that you're seeing played out right there. So I have my natural log of the base times a to the u times the derivative of u, which is that negative 3, right? And so this is my first times the derivative of the second plus the second times the derivative of the first, and the derivative of x is just 1. So we get that look right here. And then here's where you can simplify as much as you can. This one factored out the 5 to the negative 3x, and this is what would be left over. And let me keep moving through for you. So jumping down to our last couple examples. So we have another product rule going on right here. So again, we're going to do, this is our first term, and this is our second term. So we have our first times the derivative of the second, right? And so the derivative of the sine of e theta, derivative of sine we know is cosine of that item, times the derivative of the interior function, plus the second times the derivative of the first. So again, we're right back up to the rule we just looked at up above. So the derivative of this one right here takes us right here. This was the natural log of a. This is a to the u, and this is the derivative of u. And then as we clean that up and do a little factoring on that, we get this look right here. All right, here we go. Final two examples. So this one is really just a reminder to expand your logs before you try to differentiate these guys. So we got our log base 8. So I have this guy on top. I got this guy on bottom. So I want to separate those out with a subtraction since they're being divided, and then you can differentiate from here. All right, so you can see how this one played out. It's really no different than ones we've done earlier. It's great practice, so you can give it a shot. This is just a reminder to make sure you take this step before you try to use the differentiating rules. And then last one down here for example 5. Again, same idea. I want to expand first before I try to differentiate. Okay, and so as ugly as it might get, we're going to take these guys and we're going to expand it so that it looks like this first. All right, so we want to get this look. Then you can try to differentiate each one. So feel free to give this one a try on your own. See if we can get this look right here. So again, a lot going on there, but this is just how that one plays out because you have so much going on with each different log. So give that one a try and see if you can come out with this final look.